Hi, it's time for another math easy solution. Turn to discuss further into partial fraction decomposition, and now look at the general case for linear factors, a proof. In my last video, I went over a simplest case, and basically I went over for the proof for decomposing in my last video. Rational functions for the simplest case of having proper fractions with linear and non-repeating factors such as the following example. So I went over a proof that would solve these kind of examples, whereas you could see here all of these are linear factors in the denominator, and they're all non-repeating, so they're all unique. You don't have x plus 2 squared, for example, so they don't repeat. And now if you look at these are proper fractions, so the degree on the numerator is going to be less than the degree in the denominator. So in this case, you have an x squared degree, or degree 2, versus the bottom, which is, well, when you multiply this out, you'll have an x cubed. So this is proper fraction right there. And this one as well, this example here, as you can see here, x plus 7. This is, again, non-repeating, and it's linear. It's just x. There's no x squared. And then the degree here is going to be, well, x on the top, and then these multiply x squared. So again, this is a proper fraction. Yeah, but what if the factors repeat? Well, such as this example, x plus 1 divided by x minus 3 squared. So as you can see, this repeats, and it's also proper because it's going to have an x squared at the bottom, and the top's x degree only. So we know from our earlier videos that this would basically, you would write down in partial fractions like a1 basically, or a plus b. So we'll have an a here, x minus 3, then plus b, and then you'll have an x minus 3 squared, etc. And if this was, let's say, cubed instead, you would have to go now c plus x minus 3 cubed. So as you can see, this is how I've shown in my earlier videos, but now we want to prove this. Yeah, so if we were to write this out in the most general way we can, so the general case with linear factors, including repeating factors, we would write it as, let's say this, so n of x over x minus a of 1 right here, the power of n1 times it by, and we keep going on and on until we get, well, x minus ad. So this is the factor over here, where n to the power of d right here. Yeah, so in the middle we'll have x minus a2 times to the power of n2, etc., all the way to nd. So you could have as many repeating factors as you want. And now if you were to solve basically the general case, we have to prove is that this equals 2. Now we'll have it like this, a1 dash 1 as the coefficient, x minus a1, now plus a2 dash a1 dash 2. The reason I'm doing this is because we're gonna have to do this for every single one of these factors. So we get right here x minus a1 squared plus, etc. We keep going on and on until we get a1 all the way to d. Actually not d, we get all the way up to the n1th degree, so n1, and then we divide this out by a. This is going to be now yes, it's still a1, power of now n1. So just like this one here, where there's an x cubed, we go, this is power of 1, power of 2, and then power of 3. And this one we go all the way to power of n1. And then we do this, keep doing it for every single one in between here until the last one, which we get now, which we'll call this a d now. So use that, and now the first coefficient of that, x minus a d, plus it's we keep going on and on until we get a d all the way to n to power n coefficient d, and then we have x minus a d power of n d right there. So now this general case, basically the AIs are all unique, so they don't repeat itself. yeah, so they don't repeat itself. For example, since this is 1, you don't have this as 1 as well, this AD, you just combine it with this. So, and then the n of x is just a polynomial with degree at most n1, n1 plus n2 plus all the way at nd minus 1. This makes it a proper fraction where the degree of numerator is less than degree of denominator. And the reason we're adding these up is because, like I showed above here, this one here, this is this degree at the bottom is an x cubed or a degree 3. So for example, if we had, let's say, let's call this n of x at the top, then the bottom is x minus 1 it's squared, x minus 2 or x minus 3 cubed. Then the denominator here, because we're multiplying it out, this is going to be, well, a degree at the top of it has to be less than degree at the bottom. So this degree at the bottom is going to be the degree of, well, we have to look at this. This is going to be x squared, then plus x3. So we're adding these two up, which is x5 or degree of 5. And that equals to, well, 2 plus 3. So exactly what we're doing here. And then this one here, degree at most, which is going to be, well, 5 minus 1. Or all of these add them up, minus 1. So that it's proper fraction. So now that I've written down this general case with linear factors, so I've written down this theorem, and now we have to prove it. And to prove this, like I showed in my earlier video on the simplest case, we first have to prove a similar form, and we'll call that basically lemma 2. The lemma 1 was my last video. Lemma is just basically subsidiary or secondary theorem to help out in the overall theorem, which is, well, right here, this whole thing. So basically lemma 2 states let n of x and d of x be polynomials of degree n and d respectively, where n is less than d plus m. And suppose that a is not a 0 of d of x, which means you could, d of a is not equal to 0. Then there's a polynomial p of x of degree of p, which is less than d, numbers a1 all the way to am, such that, this seems a bit too much to take in right away, but I'll get to this all, I'll explain this all. So we would have to have, basically this lemma states that if you have all these stuff, it would be in such a way that you have n over d of x times x a power of m equals p of x. Now this is going to be d of x, and then we just have to prove this lemma. So plus a1 x minus a plus, well, a2 x minus a squared plus all the way until we get, well, am and x minus a, and then we have power of m right there. So basically what we are trying to do is, in this case, instead of dealing with, let's say, this general one where we have all of these different repeating factors multiplied together, we basically take one repeating factor and then multiply basically everything else we would consider as a function d of x, where it has a degree of d. Yeah, and like in my last video, basically what we're going to do is, once we prove this lemma 2, we could use this repeatingly and to solve the bigger theorem. So to prove lemma 2, to prove this, we first need to find, well, we need to just show that we can find polynomials p of x and the numbers a1 to m, so that's all we have to do. So first let's multiply both sides of this by d of x times x minus a. So when we do that, this left side, this cancels out, so we get basically n of x is equal to p of x, and now the d of x will cancel, times by x minus a power of m. Now here we get an a1 times d of x, and now this is, again, we're going to have now an x minus a, m minus now 1, because there's an x minus a there. So we keep doing this all the way, so we get now, well, a2 d of x times x minus a. Now we have an m minus 2 because there's a power of 2 at the bottom. And then we keep going on and on. So let's say plus, etc. Keep going on, plus Yeah, let's get to now the second last term, which is a m minus 1. And then when we do that, this is going to be, well, d of x. And now at the bottom will be m minus 1, so we get x minus a m minus 1. So when we do this, this just equals to, well, m minus 1. That equals to the m's will cancel, and then the 1 becomes positive. So I'll just write that. So we just get a 1 right there. Now, well, and I'll just erase that because you don't need to write a 1. So now the last part is just going to be am times by dx, and now this whole thing cancels out because we have an x minus a, m minus m, and then these, well, equals to 0, which this whole thing equals to 1. So we can just erase that. So we get this right here. Now notice that there's an x minus a in every term except this right here. So if we let basically, or at x equals to a, what we get in all of this is an na equals 2, and now all these become zeros. 0 plus etc. except the last term, which is going to be am times by d of a right here, because there's x minus a minus a is all 0 everywhere. So what we get now is am is going to be, well, n over a divided by dA, and now this bottom part right here can't equal 0, so we've basically shown that for the term am, the number, we have found this number. Yeah, because n of a is a number and d of a is a number, and d of a doesn't equal to 0 because we imposed that on this theorem just so that the bottom here we did not get a not defined function. So that's what we get. And now what we could do is basically move the am d of x on the left side, or to the left side. So to the left side. So when we do that, we get basically here n of x minus am d of x. And now this equals 2. We would write all this down. Yeah, and here I basically copy and pasted this exact thing just over here because just to save time in writing. So when I put all that, basically I put everything over here. So, and then I just move this am dA on the left side. So now when we have this part, yeah, so now let's take a look at this side right here. So if we put this down here, nx am dx right here, this whole left side, if we were to, let's say, let it equal to n1 of x and then times it by x minus a right here, so we just let it equal to that. So this is, and then we choose this n1, so I'll just say let, and so basically I'm letting this whole thing equal to this. So what we're doing is here on this left side, we know that this d of x has a degree of d, and now this n of x has a degree of, yeah, let's scroll up to see what the degree is right here. So n of x has a degree of n, where n is less than d plus m, and the reason it's less than d plus m is because if this is a degree d right here, and now this degree m, because you have an x right there, so x to the m, it has to be less than addition so that it's a proper fraction. So it just needs to be proper. Yeah, just so that we have this whole thing as a proper fraction. So that's why it has to be less than the addition of these two degrees, d and m right there. Yeah, so degree of, well, n, which is, or a degree of at most n plus m minus 1. I mean, no, d plus n minus 1. So what this means is, because you know it has a degree of n, so it has a degree of n, but n is less than d plus m. So because it has to be less than this, so it's at most d plus m minus 1. So 1 degree less than d plus m at most right there. Yeah, so now what this means is if this degree is at most d plus m minus 1, then this whole thing right here, or I'll circle this. So both these, yeah, this whole left side has a degree of at most well, the degree of n right there, of at most d plus m plus, minus a, because we're adding degrees, or x plus, no, x to the powers of whatever, so whatever the highest, that's going to be our highest possible. But now if we're letting it equal to n1 times x, where this is just a polynomial, x minus a, so what we're doing here, this has a degree of 1 right here. So what we're doing here is, if this has degree of 1, then this n of x is a polynomial with a degree that we're imposing of, now it's going to be, well, of at most, because there's a degree of 1 where we multiply it, and the whole thing has to be at most d plus m minus 1. So it has to have a degree of at most d plus m minus 2, or basically minus 1 minus 1, so minus 2. Because we are subtracting 1 from the whole degree, because we're multiplying by x minus a. And the reason we're letting it equal this is because everything here has an x minus a on the right side, and if we equate it, we can cancel an x minus a. So let's put that right here. So this equals to now n minus x, and this is x minus a. So n1 is just a random polynomial we chose, and now we've defined that it has degree at most d plus m minus 2. So if we do this, and now we divide everything by x minus a. So I'll drag this here. Now divide, divide both sides by x minus a. So what we get is on this, and then move this on the left side, so what we get is just n1 of x equals 2, drag this up, p of x. Now we have an x minus a m minus 1, because we're dividing by an x minus a. And then we add this plus, plus a1, now that has a d of x, and this was had an x minus a of m minus 1, so that's going to be, well, m minus 2, plus, etc. We keep going on and on until we get the second last term, which is going to be, well, m minus 2, because our new last term is m minus 1. Now we have a d of x, and again, because we're dividing by it, the last term is going to be, well, x minus 2 minus 1, which is equals to 1. And then we have the last term, which is going to be, well, am minus 1, and then d of x, because now we're canceling this right here. So when we cancel it, we just get d of x. So now that we have all this, and then similar to the first step, we will basically solve for am minus 1. So at x equals to a, we get n1 of a is equal to, and then these all are cancel because there's x minus a, so a minus a is 0, so we get 0 plus 0, etc., all the way into the last term, which is going to be am minus 1 times d of a. So what this means is we've solved this number am minus 1. So am minus 1 is equal to, just rearrange this, n1 of a divided by d of a. So we've got this number. And now what we could do is keep, well, repeating this. So if we look at where this ends up at, move this to the left side, so we get, now what we could have is an n1 of x minus a m minus 1 times d of x right here, and now this equals to, well, this whole right side. And here I've copied and pasted this whole side all the way down here. So as you can see, if we move it to the left side and we have this right here, similar to what we just had done, we would again let this basically let this equal to n2 of x, and then times it by x minus a. So we let it equal to a form like this, n1 x minus am1 right here, d of x. And now basically we know that this whole thing, the degree is at most, is going to be degree of at most d, of at most d plus m minus 2, because that's, well, what we had for n1 right here. And that is right here. Degree of at most n plus, d plus m minus 2, which is the overall thing right here. Yeah, because we're dealing with, because with this is at degree of d plus m minus 2, this is just degree of at most d, or that is degree of d, but we're having a plus m here. So this is the highest, and then when we subtract 1 degree with this x minus a, this n2 becomes, well, degree of at most 1 minus this whole thing, d plus m minus 3. So we do that, and then we keep repeating. So keep repeating until we get the final part where it's equal to. Yeah, and by keep repeating, I mean then we're gonna have to divide everything by x minus a again. And in this case, we've just shown that there's an n2 of x. And then we keep doing this, we will eventually get, let's go up to n of m minus 1. And the reason we go to n minus 1 is because, well, we started off with, n, so we'll call that n0, so n, then we had n1, n2, etc., and this is n2 right here, etc. So we keep going on and on until n m minus 1, which all these here is just m terms. So keep repeating 4 m steps, so we keep doing that until we get here n m minus 1 is equal to p of x. And now we have this xa. Let's start from the very top. So we got this x minus a of m. So we got xa power of m right here, but we're dividing it by, well, this is m minus 1 times. We're subtracting this now by m minus m1 right here, which is exactly what we have been doing. For example, this n1 here, this equals to x m minus 1, and we basically have m minus this coefficient 1 right there. In this case, we have m minus 1. So when we subtract this part, and now we have to add, well, the later term. So as you can see here, we get all the way up to, well, a1. That's gonna be, right, look at this one here, a1 times it by d of x. Now this is going to be x minus a, and as you can see here, we start off from the very beginning at m minus 1. So m minus 1, then we have divided by, well, m minus 1 times. It's m minus 1 minus m minus 1. So we subtract that from that. Now we don't go any further, because as you see, we always started decreasing one of the terms. So we started off with this am, then this am disappears, and we get am minus 1. So we do this all the way until we get to a1. So now if we add up these and add up these powers, so nm minus 1, p of x, this is just going to be m's cancel, this negative is going to be positive, so we get x minus a. Now plus this last term, a1 times it by d of x. Now again, this is m minus 1 minus m minus 1, that goes to 0, this whole thing becomes 1, so we just are left off with this. So now what this means is now we can go at x equals to a, we get nm, this is of x, nm minus 1 of a is equal to p, actually no, this goes to 0, this is a minus a is 0, and then we get a1 times by d of a. Solving this, we get a1 is equal to nm minus 1 of a, all divided by d of a. So as you can see, we have proven all of the numbers a1. A1 all the way to am, because as you can see, we've shown that, scrolling back up, we show that am minus 1, we showed what am is, and then we keep repeating, we get am minus 2, am minus 3, etc. all the way to a1. So we're just working backwards to solving for a1s. We've shown all of these numbers, and now what we could do is if we were to write this p of x, write p of x on its own, so we have p of x and then times it by, well, x minus a, and then just move this to the left side, so we get equals to n m minus 1 of x minus a1 d of x right here. So multiply d of x. So what we have here is, so once again now, let's look at the degrees of this. Is degree d, and now this one right here, this is degree of at most. That's the degree of at most. And now let's look up what the pattern was. We had at n2, that's degree of md plus m minus 3. So it's always one less than this pattern here. So this would be degree of dm plus m minus, now there's a 1, and then we minus again this m plus m minus 1. So what this equals to, what this equals to is d plus m minus 1 minus m plus 1. So this m's will cancel. M's cancel and the 1's cancel. It's degree of at most d right here. So basically this whole thing has a degree of d right here. Or at most d. Degree of at most d or d, doesn't matter which one it is. So what this means is if we have this, and now this is degree 1, degree of 1. So then if this whole thing, the left side has to be degree of d combined, this p of x, what we could do is, this is degree of, degree of at most d minus 1. So what this equals to is, we could let n of m, or p of x, is equal to a polynomial n of x, and this has degree of at most d minus 1. So so what we showed before is this also degree p, so p is less than d right here, and that's in the proof. The degree of p is less than degree of d, which is the same thing as saying d minus 1 right here. So thus, if we recap, so now we have found that p of x is a polynomial, degree of at most d minus 1. So thus we have shown that so we have found that there are possible numbers of a1 all the way to am, and polynomial p of x with degree of p, which is less than d or at most d minus 1, and such that basically this. So we've just basically proven this theorems, or lemma 2, such that you have n over x divided by dx of x minus a to the power of m equals p of x divided by d of x, plus now you have the a1 over x minus a all the way up to am divided by x minus a to the power of m. So now let's finally go back to the previous theorem that we're trying to prove. So when we have this right here, n of x divided by x minus a1 power of n1 times by all the way, keep multiplying the repeating factors until x minus a d power of n d. Now we can apply lemma 2, but the trick is we let d of x equal to x minus a 2, and this is 2, multiply it, and all the way keep going on until we get x minus a d and d right here. So what we're doing is basically separating one of these x minus one of these repeating factors. So we let m equals 2 and 1, and we let a equals to a1 right here, so that we get this written as exactly n over x. So n over x, x minus a, this is going to be m, now we have a d of x right here. So that's all we're doing, is doing it this way. So when we do that, we get yeah, we get n over x, and now we get x minus a 1 n 1 times by, keep going on and on, x minus a d and d. This equals 2 now. What this equals to is, well, we could separate this entire, so we get this entire part from it, which is going to be our a1 1. This is going to be x minus a1 plus, keep going on until we get a1 of n1 divided by x minus a1. This is going to be n1 right here. And now we get plus p of x, and then this divided by, well, divided by, this is the d of x, which is going to be x minus a2, this square, this is n2, and times it by, keep going on and on until we get x minus a d n3. N d right here, not 3. Yeah, so we've solved for the first part, and now what we could do is take this, and now what we could do is keep repeating. So now we repeat again, yeah, but with this time we use but with n of x equals to p of x, and then we have our d of x is equal to our, now it's going to be x minus a3, and 3 times it by, keep going on and on, x minus a d and d, and then we let our m equals 2 and 2, and our a is equal to a2. So we do the exact same thing. We remove one of these at a time, get one of these until, so we keep repeating, yeah, keep repeating but with this, and then repeat again. Yeah, so repeat until finally, yeah, so repeat until we finally get the final answer, which is, yeah, so we keep repeating until we finally get all of this, which is the theorem we were trying to prove right here. And then the last part is AD1 divided by x minus d, AD all the way until we get AD of ND, that term of x minus AD and d. And now just a note on this last term right here, note on last step. So in this last step, what we're dealing with is basically, because there's no extra, what's it called, p of x, so where does this go right here? So we have to find out where it goes. So note on the last step, if we were to write it as, let's say, y of x is equal to, yeah, let's say in the last step we get y of x equals to x minus, and then the second last term, which is a m minus a d minus 1. Yeah, and then this is going to be, well, n, yeah, this is n d minus 1. So second last term, and then this is x minus a d, and then n d. So now here it depends what we choose as the d of x. Let's say we let this equals to d of x. So if this equals to d of x, and then we get basically over here equals 2, then this thing is what we expand out. So we get a of d minus 1 1 over x minus a d minus 1. So this is the second last repeating factor, plus all the way to get a d minus 1, and now we have up to d n of d minus 1 over x minus d minus 1, and now n d minus 1. So we add this, plus we get now, let's say z of x, let's call z1 of x. So we get z1 of x, or actually we'll call it p of x. Let's say p1 of x. So that's what we get, is p1 of x. And then we get, and this underneath this is going to be x of a, d, and d right here. So we get that, but if we chose d of x equals to, instead of this x minus a d power of nd, as x minus a d1 and d1, then we get a different answer right here. So we get this whole thing, is equal to, now we get a of d1 x minus a d plus etc. plus ad, now we have nd x minus ad and d plus now p2 of x all over x minus a d minus 1 of n d minus 1. So as you can see here, we basically have these two terms right here. So what this means is that this right side, basically we could let this equal to this, so equals to, and then this whole left side equals to this. So then when we combine them, we get, what we get is the combination of the two, and the reason they're equal because as you can see, this x minus ad minus 1 only occurs on this left side, and this whole right side is dealing with x minus ad and d. So separately, you could just solve it as well like that. So what that means is at, let's go at y of x or n of x, doesn't matter, of x minus ad1 and d minus 1. Yeah, so basically these last two terms equal this. I just copied and pasted these on here. So this explains the last step and why there's no p of x right here. So anyways, that's all for today. Hopefully you'll learn from this pretty extensive proof video on this, and hopefully you are able to follow through for this pretty long video. Anyways, that's all for today. Hopefully you'll learn from this, and like always, you can download these exact notes in the link below, and stay tuned for another math easy solution.